All right, let's get started. It's going to be a fairly dispersed lecture. It's titled "The Future of Data Science," but really only a short part's going to talk about that. I'll talk a little bit. I'll just show the outline here. First of all, close up a couple of loose ends that I had from last time. Things I had realized I should have described a little better. Just one actually, but deal with that first. Spend a little time, not too much time, despite the title of the lecture, talking about what I'm calling the future of data science here. So I think it's always worth it, now that we've come kind of full circle in the course, it's worth thinking about the bigger picture of data science, kind of what that means, what kind of things you might want to look at going forward, and what directions there are for data science work. Then I'll talk, probably actually the most useful part of this lecture will be talking some more about data science at CMU. So I'm going to give a quick overview of some other potential courses you can take, as well as ways to get involved in research at CMU. Actually including, though I'll post the announcement shortly on Piazza, but including a follow-on kind of independent study course to this one. A lot of people have asked about this, so I was going to make actually a more formal venue for that, and I'll talk about that briefly. I'll do some Q&A if we have time. There were a couple of questions that people posted on Piazza. Not that many, actually. And I think actually most of them are somewhat answered already in the topics here, hopefully. But then I'll try to address some of them and also open it up to questions people here may have. And then I'll conclude with sort of some final thoughts on this course in particular, and how this course has gone, and also give some well-justified thank yous to the staff of the course. All right, so let's talk a little about loose ends. I have no slides here. One thing that people were a little bit confused about last time in my walkthrough was this notion of how I would interpolate between having no influence on the image features and a full influence on the image features. I did one sort of comparison where I normalized everything, but that wasn't really the right way to do things. And I kind of hand-waveringly said, oh, I tried some other ways of weighting it, and it didn't end up working, but I didn't actually describe what I meant by that. So let me just briefly say what I meant by that. I'm not going to type this live. I'm just going to put up the notebook with this in it. And I'll also put up this completed notebook now on the course webpage. Remind me if I don't do that by like tomorrow or something. OK. So this means it's harder to do because I have to actually find my cursor there, make it full screen, and zoom in a little bit. OK. So we saw this plot, right, where it didn't really help to have the images. Things look exactly the same when we used images versus other stuff. This was a sort of a weird plot. This is when I normalized everything. It looked really bad. Here's the plot that's maybe more interesting. So I want to combine my existing features, which is my TF-IDF features. I'll zoom in one more time. With my the price with the images. And one way to do this is to take these features here and just scale them between 0 and full weight, right? So when they have 0 weight, that means they are basically, we know we can do 75% accuracy with 0 weight. When they are full weight, we know we did really badly. We have like 50% accuracy. And so we want to interpolate between those two. Yeah, question?
Those features you said you use VGG?
Yeah, VGG for the image features, yeah, like in the homework.
Did you have to train them all again?
No, I did not. So certainly you could do better with fine-tuning if you retuned the whole layers of the network. I just took the raw VGG images, took the second to last layer, and used those as my features without any fine-tuning. So then what I'm doing now is I'm actually going to have some weights that I'm going to apply to those image features. So I'm going to vary that. Again, you want to vary it logarithmically because these things always enter in a logarithmic scale, not in a linear scale. But basically what I'm doing is I'm just multiplying the weight of the image features by some function here. So I'm basically looking at multiplying the TF-IDF features by 1, the image features by some weight W, and then the price feature by 1, and I vary this W parameter in the same way I varied the C parameter and other things. And this is the figure I get, which is probably the more important one. So here on the left is the performance of just the TF-IDF features, right? That is when they have a weight of 0, effectively, on the image features. And here I'm varying it between 10 to the negative 5, which is effectively 0, and 1, when we know we have bad performance here. And in doing so, there's no real region where this actually improves, right? If the features improved, at least in this setting, you'd see a little bump at some point, and then it would go back down. And there's no real region where we have that here. It's pretty much all bad. There's a slight bump there, so maybe that looks good. But then it turns out when I actually took that parameter, which is about 0.004, and looked at the cross-validation error and the test error didn't improve at that level, at that parameter, over what I had before. So this is sort of just, this is just maybe hopefully making a little bit more concrete what I meant last time when I said I added them with a low weight. This is what I mean. And I'll post this notebook online so you can see this yourself. So just wanted to tie up that, because I think I did a bad job of explaining it last time. OK, let's go back to here. All right, so that's actually the only loose end from the course as far as I'm concerned. I'm sure there are others. You're welcome to ask questions on Piazza, et cetera, what else I haven't tied up neatly in the course. OK, so let me take a little bit of time and talk about the future of data science. And this is going to be very high level here, admittedly. This is going to be kind of just what I think about some interesting directions in data science, and as well as a little bit very briefly about some of my own research. Because I work in data science. I work in a lot of applied research. And I want to talk a little bit about some of the work I've done and kind of how I see data science fitting into that work. So talking about the future of data science is always hard. Talking about the future of any technology is always hard, because technology is really hard to predict. For example, I honestly don't know. We are right now in an AI boom. Everyone's talking about AI, artificial intelligence. I teach AI. So next semester, I'm actually teaching the graduate AI course. I encourage everyone to look at that course if they're interested in AI. But I don't know what's going to happen with this recent surge. So there have been in the past very notable surges in interest in AI research. Industry gets really excited about some new trend in AI. We think we're going to solve intelligence, and all of a sudden it sort of collapses. These are called AI. These have been called in the past AI winters, times when funding and corporate interest kind of collapses in AI. That may happen now. It may not. It's really hard to say. We may have reached a point where there's actual tangible value being produced by AI systems to the point where it's even if it dips a little bit in the popular press, it's never going to go away. Or it might just it might have a similar crash. We might realize that deep networks really just can't go beyond. They can't go from solving Atari games to solving something more complex. There's already some more complex stuff, so it's probably not true. But they can't cross a certain threshold. That stuff is just actually boring. We don't really care about that, and so they're going to fade away into at least for the next 20 years, and then they'll come back in 20 more years when we have better computers and even more data. I don't think it'll happen, but it might be somewhere in between. However, when it comes to data science, I'm a little bit more confident in my predictions here, because I'm pretty confident, and I'll take this bet with virtually anyone, that data science by some name or another is going to be here to stay for a while. And the reason is that it's almost, at this point, it's becoming so ingrained in how we sort of do any kind of analysis. When people talk about doing business analysis or analyzing analyzing any question, it's almost sort of second nature now to talk about using data. It would almost be crazy not to use data, right? And that really is the essence of data science. It is using data to try to answer scientific questions or answer questions about the real world. And so I strongly doubt that we'll reach a place where there's no use for data science or the things you've learned in this course. I mean, certainly there will be new techniques that supersede old techniques. Maybe there will be new libraries that you'll have to relearn from scratch again. But I really don't think that the core ideas here are going to go away anytime soon. It's not a trend that's going to reverse itself. Yeah?
Please define AI.
What is AI? AI is the broad field of I shouldn't do this, but I'll give you my answer. AI is the broad field of study which relates to creating computer software that can replicate any sort of notion of intelligence. Which that's very broad, and that's intentionally broad because AI is a broad field. If you want to know more about that, take my AI course next semester. I think that's the first question we ask in the course. What is AI? And it's actually almost like a silly question because what's much more important is sort of what these techniques can do rather than what they are fundamentally. But that's another topic. So the most prevalent way I think of data science sort of remaining a force in the future is this notion of data science for blank, right? If you have any field, there's going to be the desire to take your topics and the questions that come up in that field, not in machine learning or not in computer science, unless your field is computer science, but take the questions in that field and apply data analysis and data science to them. So and I think it's actually kind of at this point hard to find a field that is not trying to do some amount of data-driven analysis. It's very hard to find fields that are just, I mean, even like humanities are starting to do like data-driven analysis of text and things like this, right? It's very hard to find anyone that would say, no, we don't want to do any data analysis. We want to just use our intuition to guide the decisions we're gonna make. So as a little example here, these are all areas I've personally worked with, at least tangentially. So I've either talked with someone working in this area and collaborated a little bit, or I published papers in these areas. And so it's not just theoretically talked about it, but I actually did some amount of tangible work in the area. Energy systems, which I'm going to talk about a lot more because that's actually one I work in a fair amount. Building management, wind power, related to energy, but a little more specific. Material science, chemical engineering, aerospace, robotics, fluid dynamics, industrial manufacturing, fire detection, and weather forecasting. And I was actually trying to rack my brain for more. I'm sure there are actually more that I'm forgetting here. Just because these techniques are of the type where it's incredibly easy, honestly, to take these techniques, enter into a new field, and you may not have huge, sort of deep insights, but they do provide oftentimes interesting insights that people haven't really thought about, or a way of thinking about their field they haven't really thought about before. Now, that might be actually decreasing now because I think people are getting more and more skilled with these things. So you see more and more fields actually having data scientists in those fields. But you still have kind of this sort of amazing toolkit with which you can approach new problems and kind of look to address new challenges that you'll encounter as you study whatever field you want to study. So with that in mind, let me highlight a couple, just a very, very few. I'm not going to spend any time on these things, but except other really than to name them and give maybe a 2-minute description of each one. But some of my own research focuses very heavily on, I even have a little animation there. I didn't know that was actually animated in this version. Very heavily on data science and sort of these methods applied to energy and power systems. So here I mean, the electrical grid, renewable energy, really any sort of notion that we have of energy systems providing electricity or other forms of energy for the world. So one thing that I think is becoming much more prevalent these days is something called demand response, or more generally demand-side management. So in the traditional electricity grid, power was kind of considered an on-demand thing, right? Whenever you want power, you take as much as you want, and you pay the same for it no matter when you use it, or how much has to be done on the back end to actually provide that power for you. The flip side of this is that in the generation side of the world, they have to always be producing exactly as much power as people are consuming right now. That's actually a very complicated process that's completely unseen to most of us about how they actually do schedule a whole lot of dispersed generation to account for the fact that I can go over there and turn on the light if I so want to. And they have to actually provide the power for me to do that instantaneously, virtually, right? So this is a really hard thing to do. And as we get more sources of energy, like renewable energy, that cannot be controlled in the same way that old sources can be controlled, it becomes more and more important to be able to actually not just manage the production of energy, but also manage the consumption of energy in an intelligent manner. And so what a lot of places like large plants, these are large manufacturing plants, you can do this at the home level too, but it's a little bit less common there. What things like large plants are doing is actually figuring out how to schedule their consumption to provide some sort of benefit to the grid, and in response, they get paid something for this. They kind of are providing effective generation in their ability to curtail demand or curtail their consumption. One study we did was looking at cement plants. This is a cement crusher. It's the big thing that crushes up rocks to make cement. We combined that with a large industrial battery as well. This is a grid scale battery, and showed that by combining these two things and intelligently controlling turning on and off that cement crusher, we can actually get better, can provide substantial benefit back to the grid and allow the grid, and allow essentially the operators of these plants to make some money from the grid and from system operators, in addition to just making it from themselves, from their cement that they're building. I've also done a lot of work in wind turbines. So this is actually a little wind turbine that when I was a postdoc I built in my lab. It was it's like in a big hangar here. My desk was underneath it actually. And what that was is that was looking at, can we do, and I should say the theme of all of this is some amount of data-driven learning here. So on this side, we have to know, on this element here, we have to know how does the actual consumption and grid signals vary over time, and do these actual real signals allow us to effectively control the operations of a cement plant to provide value to the grid. Here I actually, as I was saying, I built a little wind turbine and did some experimental analysis of the power production of this turbine as a function of different parameters of the turbine in uneven wind fields. And I did this in a way that basically would adapt the angle of the turbine blades kind of in an online, fully model-free way to try to create as much power as it could. It was actually not just to pitch the blades, but there are other things too. You also want to vary how much resistance you put on the generator. But by varying these two things, you can control, you can sort of find an optimal region to generate the most power without worrying about building an accurate fluid dynamics model of the turbine beforehand. I've worked a lot in energy disaggregations. This is a problem that we had on our homework, so you're maybe familiar with it by this point a little bit. The idea is if you have an aggregate energy signal from some building, you want to actually try to break this down into constituent parts to give people, either to give people more feedback about what they're consuming, or to actually do things like better forecasting to figure out how people are actually going to consume going forward. Because if you know a certain device is of type A or B, that can affect how you're going to make those predictions. I've done work on using both low being like 1 hour readings from smart meters, or high, meaning sort of very, very high frequency, every second or even faster than that readings from custom hardware we install in homes. But in both those settings, I've looked a lot at ways that we can actually do this source separation problem. So we talked about one way that you talked about in class, or we did on the homework. But there are many, many more sort of very complex techniques for separating out different constituent appliances in an aggregate signal, and I've worked a lot in that area, both on the algorithmic side as well as actually on the data collection side too. So I've done a lot of work on collecting data for these things. And finally, again, not an exhaustive list here, but one thing I've worked a lot on is probabilistic forecasting. So the idea, again, I mentioned this briefly, but when you have renewable sources of energy, things like wind or solar, which are good really for many reasons, a big challenge that comes up is that they are not dispatchable, right? We can't actually control them and say, I want to turn on my wind right now because I need to generate some more power. And what that means is you have to be able to then predict them instead. You have to be able to actually predict what's going to happen at this wind farm, because you need to keep your other generators ready to go if that wind farm's all of a sudden going to drop its power output. And the problem here in forecasting of wind is that, like many tasks we talked about in this class, this is one of the ones definitely where you can never get it exactly right. There's no such thing as a perfect forecast. Maybe at the, if you could simulate the actual fluid of the fluid dynamics of the entire atmosphere at the level of a foot by 1 foot, you could do it, but that's never actually going to happen. At the level that we can model things, this will, I shouldn't say never, but probably won't happen for a very, very long time. At the level that we can actually model things, there's going to always be some inherent error or inherent stochasticity in any forecast you produce for wind. And so the big question then is actually not so much how accurate is your forecast, but how accurately does your forecast describe the true underlying uncertainty that there is in the wind. In other words, if I say, here's my distribution of wind I'm going to see over the next hour, if I predict, and if I were able to sort of, look at 10 different times I predicted the same kind of distribution, does the reality actually fit the fact that, then 10% of the time it falls into that 10% quantile, 20% falls into 20% quantile, et cetera. So how well calibrated are your predictions that you're making here to the true uncertainty of these distributions? So that gives some idea, hopefully. I mean, it's a very high-level overview, but it gives some idea of the kind of things I've worked on. From a data science perspective, I also, the other half of my group kind of does much more core research in machine learning and optimization. But from an applied perspective, these are some things that I work on kind of on the data science side applied to energy systems. So now I want to mention, I want to back up again and sort of just mention a few more kind of large trends I see happening in data science. This is not, as I've repeated many times now, this is not an exhaustive list. I think it's just when you think about the issues that data science is raising, these are important topics. And so in addition to just the question of, well, I want to apply data science to some new domain, these are some questions that encompass data science as a whole that may be really interesting for you to think about. So the first one is sort of, I mean, maybe at this point almost cliche, and you've already know that I'm skeptical about the need for big data and a lot of data science problems. Not that it isn't there in several problems, but I think that several times when people say they are using big data, or in fact do use big data, which is not always the same thing, they often don't actually need it. So that they'll use a data set of terabytes to estimate a linear model with 10 parameters. And I'll just tell you, we haven't covered theory at all, but the theory says that is useless, right? You don't need to actually have that many parameters if you use you don't need that much data if you have a fixed small number of parameters. If you just randomly sample your big data, you'll get the exact same solution to your machine learning algorithm. So you have to be a little careful about what what problems you really need big data for. But it's undeniable that we are in a regime where we're generating more and more amounts of data that we want to somehow process. And my actual sort of the area that I think is most interesting in terms of data generation are actually from automated systems. So I'm less interested in things like selfies people take, because if someone took a selfie, they probably have, I mean, they aren't going to, but they may have, someone took a picture of something, a dog or something like that, right? They probably have time, or they would have time to say, hey, this is a dog too, if you give them a little bit of insight into that. No one is ever going to go through the vast amounts of data collected by all these Internet of Things devices, all like the sensors we're deploying sort of all around the world, all like the aerial imagery data that we're collecting, satellite data we're collecting. No one will ever sift through those to find what we think is actually important. And so we need data science techniques. We need sort of automated processing techniques to actually make any use of that data. And maybe someday when we all have, whatever the successor to the Google Glass is that we're all wearing all the time, that will also probably be very boring data, right? Most of the time nothing will happen, and you don't really care about seeing someone's video feed the whole time. Can you look at that really boring data and identify automatically the important parts of that? So I think there is going to be bigger data. We are going to need more automated techniques, data science techniques that process that data. I think for now the pipeline will look something like automated data generation and some simple, relatively simple, though this is what I'll mention next, relatively simple processing to filter out and sort of find the important parts of that data. And then you'll do kind of your traditional data science analysis. But I do want to admit fully that this process, as we go forward, will be more and more circumvented, where we're just going to start doing the analysis directly in this large data when we can. We can't always do it. There will always be some filtering steps involved. But more and more you kind of want to avoid throwing away data until you've really analyzed what you care about in that data. So that's one trend, bigger data, and it will get bigger. Another big one, which we haven't talked about at all, and I kind of wish we had a chance to talk about this. I was going to have a guest lecture on this one, but it didn't quite work out the timing. And I've mentioned it briefly as well in a few contexts, but there's a lot of tension between our ability to extract information from all this data and people's privacy, right? When we're talking about analyzing data generated from people, this is sort of but even some sensors can tell you actually a lot about the people that are around there, right? So whenever we have this mass of data, there's going to be information leakage in terms of information about people themselves. Some well-known cases are this New York Times article talking about how companies learn your secrets. These are actually all both pretty old at this point. This is a more recent one. This is that article that I mentioned that talked about the woman where Target found out she was pregnant before her family knew. That I was looking into that story more, and that story doesn't really have that many quotes or that many sources, so it may or may not be apocryphal, actually. It was sort of this one New York Times article that everyone then picked up because it's such a great story. So I actually want to add a caveat there that it's reported in the New York Times. They did report this, but I don't have any other sources confirming this, so it could be because no one wanted to admit, Target didn't want to admit this, or it could be that this actually kind of an apocryphal story that kind of snowballed from there. One or the other, but it was reported in the New York Times. And certainly things like that are, things like that are happening, even if that example maybe didn't quite occur exactly as it was specified. Probably a more likely scenario, honestly, if it did happen, was that Target just made a mistake, didn't identify her, as the person to get these things, or just saw that she should get some stuff and could have accidentally sent her some other stuff, and then did end up being pregnant too. So it certainly could happen, but Target is very aware that they don't want to, give people stuff before Target tells them anything. So that's sort of also why it might be a little bit fishy there. I don't know if people, this is actually even an older story now. I don't know if people heard about this. In 2006, AOL kind of, possibly accidentally, possibly on purpose, they've kind of, it's been a little bit, it's foggy now. It seemed intentional at the time, but then they said it was accidental. We didn't mean to release it publicly or something like that. So they released a dump of search queries that people had issued. All anonymized, of course, right? This is when we were very naive about what anonymization actually meant. All anonymized. So they just have, user 2000. These are the queries they typed, and this is the websites they went to afterwards. But it turns out people often search for themselves, amongst other things. It's a very common search to do online, right? They were, people were subsequently able to really identify a lot of those people in those terms because you'd search, for things around your area. You search for yourself. You search for, even if not yourself, you search for things, related to yourself. And it's very easy to figure out, to narrow down who these people could be from supposedly anonymous logs. So this was kind of an almost insane case of doing this. I mean, no one in their right mind would have, in retrospect, would have ever just released raw search logs. No one's ever done it again. But there have been similar cases where people have taken great pains to try to anonymize data, only to find after the fact that people, by combining that with some other source, they're able to actually identify some amount of what you could consider personally identifiable information from this data set. So there's a lot of both kind of practical interest, but also research in how we can do data science analysis while still preserving some aspects of privacy that we, presumably all still do care about. Though the amount that we actually care about is actually unclear, I think. Or at least how much we care about privacy. But the question, of course, is not just do we care about privacy, it's just how much we're willing to trade privacy for convenience. And the answer seems to be we're pretty willing to trade privacy for convenience so far. A little bit related, but a different topic is bias in data science. This is actually, I think, yeah, go on. Question about this? Yeah.
Yeah, about this privacy. There was a months ago, Apple said, yeah, we're doing something on differential privacy to aggregate it in a way that we can learn from it or not identify users.
Yep. Yeah, sure. So the question is about some recent announcement on differential privacy. I don't know what Apple's doing because they're very kind of secretive about that kind of stuff. And other than mentioning the term, they probably haven't said too much. Differential privacy, though, is kind of the main keyword that comes up when we talk about the research in privacy preserving data science, right? With differential privacy, very, very sort of briefly, what it does is it essentially requires that you add noise, a certain amount of noise to queries. When you make a query, the system will inject a little bit of noise in that. And it does so in a way that actually guarantees that for any given record in your database, the answers to your queries you get are not distinguishable or or at least with high probability not distinguishable, whether or not that individual record is in the database or not. That's the formal statement of privacy, of differential privacy, or something like a formal statement of differential privacy. What that implies is you can't, because your queries do not change very much by the addition or subtraction of a single record. What this means, and they cannot change very much because of that, what this means is that you presumably cannot extract any information about that record from the results of your queries. So you can't issue a query about a specific person because that query would change a great deal whether or not that person was in there. So if you guarantee that all your queries are not able to change that much based upon the addition and subtraction of individual records, that is sufficient to guarantee a pretty strong form of privacy. Now, I think that the question that remains to be seen is how useful in practice is that really? Because a lot of like the aha moments we have, right, are frankly often gathered from some very small subset of the data, and the noise and aggregation necessary to achieve differential privacy guarantees often would mean we can't do that kind of analysis. So it's very much an open. So people know that I guess the short story was we have a theoretical framework for guaranteeing, in some sense, with some high probability, that we don't reveal too much information about users in a database. The big question that remains is, from a practical standpoint, what are the types of analyses we can do in this framework? And that goes on the name, as I said, differential privacy. So there are probably whole lectures, or if not whole courses here on that.
So there is no like a certain, let's say, consensus on the usefulness of the data you get through the privacy.
Right.
And you have to try.
Yeah. It depends on your application, and it's also a lot of work to actually do. I don't know, and I'll just say, there may be some, maybe Apple's doing some. I don't know of any fielded databases that are using differential privacy at a large scale internally inside a company, right? So maybe they can expose some external interface with this. I haven't seen much of that either, actually, to be honest. Public interfaces. No one wants to take the risk that there's some bug in the proof somewhere, and actually, it's not quite true. But I do not know of any cases where a company takes their own internal data and puts it behind a differentially private database in order to do their analysis themselves, because it's just not worth it to them, right? They would rather just have NDAs signed by everyone and sue them if they do in fact breach that contract. So it's not something that is widely used in practice yet. Did you have a question? Oh yeah, no. Yeah. Yeah, that's absolutely right. So yeah, just to repeat the comment, differential privacy is not yet widely used, definitely not at all really used in practice. And people are using much more sort of systems level controls to control access to data in a way that they hope will preserve privacy if people are honest.
Because I had questions about, like as you said, if you had that sort of noise, how could data science and how useful would it work with that sort of data? And I had questions about that.
Yeah. So the question is, how useful can you do data science? So
useful, then what's if you're gonna you can only do mediocre predictions, or
right.
will still be as mediocre as it is. Then what's the point of doing that?
So just to, I think maybe the answer, I won't repeat the whole question, but I think the answer is you can come up with certain domains where if you have a certain class of model, you can learn the exact same model with a differentially private database as you can with the other one. So there are domains, but these are frankly kind of contrived examples after the fact. I have yet to see an example that's done from the get-go in that way. Because everyone can always just look at the data if they want to, right? So they always just do that. Yeah. So a related but slightly different question is that of bias. So there was a very popular, this is actually just earlier this year, ProPublica released a very kind of, released a article as well as a data set and analysis that got a lot of press here. It's got a lot of pushback too, so I want to emphasize that there is some debate going on here about this. But they analyzed a software that's used by courts to sentence people. And the objective of the software is to determine whether or not a person was going to reoffend if they're released, or if they are, put out on a lower bail instead of a high bail, right? And the claim was that this system, the claim that was made by these researchers, is that this system was racially biased, in particular against blacks. It was very, if you would look at some of the data, and the claim was that it was giving weight to someone's race in terms of whether they were going to recommit or not, which is clearly something we do not. I mean, if we believe, I think it should go without saying, but it's clearly something we do not want in a piece of software like this. And the argument is that data science systems are built upon past data sets, right? They are data driven. If there has been a racial bias in past decisions, there's very likely going to be a racial bias in the algorithm's predictions, right? And so the argument is that these systems are, I think a reasonable argument, even if you push back a little bit on some of the details of is this system exhibiting these racial biases or not, is that this is something that's not ever understood, and we don't analyze it thoroughly for our existing systems. We just put them in use. Some company hires a big consultant company to write the software, or sorry, the government hires a big consultant company to write the software. They deliver something, and they just use it without any audit of whether or not this software is exhibiting these biases. So this is an incredibly important topic, I think, as we turn our lives over more and more, or not our lives, but if we turn aspects of our lives over more and more to these data-driven decisions, we should be asking, are there inherent and immoral tendencies, the things that we would associate with immoral behavior and unethical behavior, are those being evidenced by these systems that we build? And there's just because they're an algorithm, right, that can't have innate bias, doesn't mean that they're not going to exhibit bias, because, as I said, if they're built upon data that has that bias, they are going to very well keep on recreating it. So this is a very recent work. They also have all their data, by the way. So they released their data on this. So this is actually a very cool bit of analysis. And if you want to do follow-on work, it's a great sort of source. The links here on tackling some of these issues and thinking about some of these issues. And there's also, I should say, a lot of academic work now trying to say, like with privacy, right, trying to say that if we can, if we have certain features that we want to guarantee the algorithm is not biased based upon these features, how do we ensure that this is in fact holding in our population? Because there can be correlation, right? There can always be these hidden variables that we don't know about that makes the things very hard, but we want to ensure that we're not directly using some sort of racial bias or any other kind of bias for that matter. Okay. So let me now talk a little bit about, I think actually one of the biggest questions I got at lunches was, what other courses should I take after this course? So I do not want to limit your search at all. There are more courses related to data science that I could ever kind of describe here, including one I think with the exact same name as this. I wasn't aware of this when I started, but there's another course called Practical Data Science. We'll have to see how that works out long term. It's a mini course in Hines though, so I don't think there's too much risk of confusion. But it's kind of funny. I didn't know about it at the time I named this course, but it has an obvious appeal to this name. So, but other courses, I'm actually going to focus. These are courses that sort of I know a little bit about. So there's many that, including the other practical data science course that I know actually nothing about. There's many other courses in other colleges that I don't know very much about. This is largely biased towards SCS and a stats course, and stats because I know some of the courses in stats. As I said, it's a very non-exhaustive list. But the high-level picture here is that really CMU is kind of an amazing place, and that there is a huge number of resources you can take advantage of if you are interested in data science. Now, I think that for the most part, a lot of these courses will be more specialized than this one. So this one's intentionally very broad. It's meant as an introduction to data science and as a sort of, as the name implies, a practical tutorial on how you use some data science. some of these are much more detailed. For example, the machine learning courses, of course, focus entirely on machine learning. But I did want to put up some ones that I think are worth, that I know about, that I think are worth looking into if you want to continue along in your research on data science. And again, which one you take here would depend largely on which directions you want to pursue in data science. And these are also, I should say, these are heavily biased towards kind of the analytics side of data science. So there's many, many more courses that kind of deal with much more of the databases and the cloud, like cloud computing, distributed systems. These courses are out there. They're not listed here, but they definitely are important as well. There's actually a program, a master's degree at CMU called the Master's Degree, or the Master's in Computational Data Science, so MCDS. If you look up that program, you can go through their syllabus and see other courses that they have a track that's more related to the system side of things, so you can actually look at that system side if you are more interested in that. So to name a few that I think kind of relate to the analysis side of things. Of course, 10601 and 10701, those are the machine learning courses. 10601 is the supposed MS level 1, whereas 10701 is the PhD level 1. But there has since been even more, that was not advanced enough, or too many people were taking that course, I guess. So they since added an even more advanced machine learning course, which is 715, which is really advanced now. So people ask me about these two courses, and my advice would be, I do, and actually I'm curious what people think here that have taken them. I would estimate if you've taken this course, you would be capable of taking 701 after this course. If you took it and kind of understand the material in this course, understand the machine learning, I think you'll be capable of taking 701. Don't hold me to that too much. And if you struggle in some of the machine learning stuff and really didn't quite get it, maybe 10601 is a much better fit. But certainly 10601, you're definitely capable of taking now, and I believe probably 10701 too. So I'd recommend people look into those if you do have interest in machine learning. Of course, it's a little bit less well known, but I think extreme that I would emphasize maybe even more than that is a course in statistics called Advanced Data Analysis, and this is the undergrad number. So this is 36402. This is taught by Cosma Shalizi. I think that's how you pronounce his last name. I should have made sure of that. But and this is essentially, the way I think of this course is, this is essentially a much more statistical view of a lot of the same things we talked about here. So I'm kind of giving you a CS style view of a lot of these topics. That course will give you the stats view of these things. So you'll learn R instead of Python, for one. That's the big differentiator, of course. But you'll also think about it from a much more statistical perspective and kind of look at these things from the context of statistics. He has analyzing data, maybe less about cleaning data and processing the data, getting the data. But once you have the data, how do you think about statistical techniques to analyze that data? He also has a fantastic textbook that goes along with this course that's available for free online too, so I'd recommend checking that out as well. And I think it's a really excellent course. The 5839 is the Interactive Data Science course. This is the one that Jen Mankoff is teaching. She gave a guest lecture in this course on data visualization and interactive data visualization. That course gets much more into the details of sort of how do you present interactive stories in some sense from data. I don't actually want to speak too much about what it's about because you should just go check out the description. But it's a lot more about visualization, a lot more about kind of building interactive ways of looking at data than this course has been. Then there are a bunch of what I would call kind of machine learning-esque courses that I'm putting here again because I tend to lean towards that side, so I know more about these. I think that if you lean more towards the system side, you want to check out those courses instead. They're not listed here, but you should definitely look at those instead. But from the machine learning standpoint, some of the more well-known ones, I'll say, are 10605, which is the Machine Learning with Big Data Sets course. I believe not offered in the spring, so unfortunately you can't take it next spring. The 15826, which is Christos Faloutsos' course on databases and data mining. 15708 and 780 and 781. Those are the artificial intelligence courses. I'm teaching 780 next semester. Actually, despite the numbering, that's the topics one, whereas 781. So in 780 we cover more topics based upon who's instructing the course, whereas 781, we teach the same syllabus each time around. 781's taught in the fall, 780's taught in the spring. So if you want a broad overview of AI, 781 is probably the better one. If you want to, if you know certain faculty and know that you want to learn about their area, so like I'll cover a lot of optimization, a lot of machine learning. My co-teacher next semester, Ariel Prakashi, is going to cover a lot of game theory and social choice. So if you want to focus on those, then take the 780 course. Then there are a variety of other ones like the deep learning course and the machine learning for text mining course. Those I actually know a little bit less about, but I know enough about them to know that they're probably worth taking if you want to either do text mining or want to do deep learning. Take those courses. So that's a very non-exhaustive list. Hopefully it gives you a start about where to go from here. But it's, again, by all means, if you say, what about this course? I'll probably say that's a great course to take too. So you should take that one as well. You had a question?
How would you compare 36402 with the other stats courses, which is 36700?
36, I believe 36700 is quite a bit more theoretical. So this one is much more kind of hands-on. This is really a data analysis course. How do you analyze data? And that's the big difference I see. But I could actually be a little bit wrong there because I'm not super familiar with all these courses, whereas 700 is a little bit more of kind of a standard statistical theory and statistical kind of, here's statistics kind of course, where this course is really about data analysis. Yeah?
What about 701 and 715?
Yeah, so 10, 715, if you are a PhD student and you want to really dive into machine learning as a research topic, 715 is great. If you want to use machine learning, don't take 715. Not because it's bad. I mean, it's a fantastic course. It's just that it is a course built for the first year PhD students in machine learning. They will not, I mean, they had to create this course because that was 701 originally, and it got flooded with other people. So they will just move on to another course number if people keep flooding it. So if your primary goal is to learn how to use machine learning, don't take that one. If you want to know the theory of machine learning and really understand, and build a platform for doing research in machine learning, then you can do it. But that's if you get in. I think they're pretty strict about who they let in too. You have to really demonstrate that you are actually in that category for someone that wants to base your research going forward on machine learning. But if you do, then it's a great course. Yeah.
This course is AI and it's going to be recorded?
Graduate AI will be recorded, but it won't be like this where you can only attend the video lectures. We're going to have actually in-class quizzes where you have to actually be there. So that means also we can't, this is sort of a joint, I mean, I'm working out, co-teaching it, so we have to decide on this together. That means we will be able to, so it has a very long wait list right now. And there are only, I think the room size is like 108 people in the room. And that will certainly max out by the time this course starts. My strong suggestion is if you are genuinely committed to this, stick with it, because I will guarantee you the course size is not going to be 108 by the end of the semester, so you'll be able to get in. But it will take a leap of faith to stick with it until you reach that point. But I promise you, it will not be as big as it will not be full by the end of the semester. I will bet anyone that yeah. Yeah. We will use AutoLab, yeah. But actually not as much. So each homework will have one theory question and one programming question. So or maybe more than one. So some of the assignments, so it won't scale as easily too. So we need more TAs. So that's the other reason why we can't let in everyone. But we will use AutoLab for the programming assignments, yeah. Okay, so now moving beyond this a little bit, so that's courses, but what about research in general? I think people also, the next question they have is, I want to get involved in research at CMU. What do I do? Well, so the first thing I'll say here is that data science itself is not really a topic of academic research. And the reason is that usually the research that involves data science is actually research in whatever area you're studying. So if I'm doing data analysis in energy systems, that's not data science research. That is energy systems research that applies data techniques to it. Or maybe machine learning research if I'm developing, very advanced machine learning techniques for that. So the academic work that probably is closest to to data science, at least as I've presented so far, would be kind of one of two types. There, first of all, is fundamental research in machine learning and statistics. That's actually what a lot of my group does, for example, is kind of, we don't just look at boosting a whole lot and see different techniques of boosting. We develop actually new techniques and new algorithms rather than just studying existing ones. And then we use that and we apply those to data science applications or data science-like applications. That's kind of what the research in my group often does, or sometimes it's kind of purely foundational research. The one bit that kind of crosses this, and I should say, this is kind of what I do, but there's also similar research in like distributed systems. So there's plenty of research in tools like big data tools. So Spark is now one of the most well-known big data platforms, but as of 2012 or so, it was academic research coming out of UC Berkeley. So there's plenty of research on that side too that relates to data science, but those really fundamentally are kind of core research in the areas that end up having application in data science. That was not published in a data science conference. That was published in a systems conference, and most research I do is published in a machine learning conference, not in like a data science conference. There are data science conferences. I don't know what they're really about, to be honest. I think they're still trying to figure out what they're actually about. The one thing that is a little bit crossing this divide, though, is what I'll call methods in automating data science. So there's this whole trend also to like take everything you've learned here, like every other field in computer science, and make it useless, right? By having a computer that can do just as well as you do at solving these problems. There's one example of this is a tool called the Automatic Statistician. That's a tool out of Cambridge that has, and collaborators, I should say. Some people at Toronto as well were working on it for a while. But this is sort of a suite of tools that basically looks at finding relationships in data in an automated way. So taking what currently requires you to look at data and visualize it in interesting ways and trying to automate that. Now, I think that's just kind of to a certain extent, maybe a fancy way of just saying it's just a little bit more advanced machine learning. I mean, machine learning tries to find patterns in data too. But this sort of spans the gap between things that traditionally were very hard for algorithms to do themselves with things that were, and things that have in the past required humans to do, and trying to push that more towards what's actually capable in an automated way. So my advice is, if for those that want to get involved in data science research, you sort of have, you have a few avenues. I think I have another slide on getting involved in machine learning, or another bullet point here on machine learning research, but I'll just mention it. My advice would be, if you want to get involved in data science research, find someone that's doing research in the applied area that you care about. And the good news is that at CMU, there's going to be a lot of those people. So if you care about material science, there's a whole department on material science that will be more than excited about you taking these techniques and applying them to material science. Now, the big caveat here is you are not going to come in as some savior and know nothing about the field and revolutionize it by applying what you've learned in the course so far. You will have to, in addition to learning more about data science, you'll have to also learn and invest a lot of time in learning the actual field itself. But if you do that, the combination of these two things can be incredibly powerful, and it really can revolutionize fields. So if you want to do applied research, find someone in that area. Don't strike out on your own and say I'm going to change material science. Know nothing about that. I'm just going to do it with data science techniques. Go to talk with people there. They're right down the hall that way. And take that approach to dealing with these things. If, on the other hand, you want to do fundamental research in machine learning, talk to people in machine learning, right? But be aware that if you want to do research there, the research itself is not going to be about answering data science questions. It's going to be about developing new algorithms or new theory that kind of can answer those questions. And that is going to be the topic of research. Statistics kind of can actually vary between those things. So there are some statisticians here that will do very applied work that is still research, and so that might be the most similar to this in some ways. But there are also some, of course, that do very theoretical research that's even beyond the theory that's done in machine learning. So And if you want to do systems, go talk to a systems faculty, right? But that would be my general advice for getting involved here with research. However, one more thing I do want to add though, which is an opportunity that I hope some people will take advantage of. So I've had several people ask me in this lecture, in lunch or some time afterwards, about the possibility of some independent study afterwards, which I'm very actually excited about doing. And if you're interested in doing this, I would love to. However, I got enough of these that I think it actually would be more efficient to have another course for this. So in the spring, I'm going to be offering kind of a independent study type course. It's going to have its own number. It's going to be like a research. It's going to be 12 units. It's going to be kind of a research focused course. We will have a few meetings throughout the semester, but the majority of it will be an independent study type course. So you're going to be required to do the work on your own for the majority. We'll have occasional meetings as a class, but that won't be the focus of the course. And the idea here is it's something like the class project, but in much more detail, right? A chance to really take these things and apply them to some real problem. I will be much more discerning about the problems I allow people to work on there. For the project, I'm very open about things. I had people change their topics very, very infrequently. But I probably won't, for example, let people do like movie review prediction. It's been studied to death at this point. I don't think you're going to, in a semester, produce anything that's interesting or new in the area necessarily. So I won't let you do, collaborative filtering for IMDb movies for that project, right? It has to be something attacking an actual new problem. I'm happy to suggest problems that I have come across in my own research. I can give you data and problems that we've looked at, but you're also welcome to come up with your own. And so I would encourage anyone that sort of really wants to pursue a little bit more research in data science, doesn't quite yet know what they want to study. Maybe you're not quite ready to find an advisor in another field and kind of jump into that. Though if you do, by all means, just go do that. But it'll hopefully be kind of a little bit of a middle ground where it's more than just this course so far, but not quite the full immersion in some applied area. You can, by the way, also have a collaborator in another area. If you want to use data for some other area, that's certainly fine. And the goal will be to do something, actually to produce something, the only goal actually of the course, because it's research units, will be to produce something tangible, like a data set that you release publicly on GitHub, along with a big post or article describing your analysis of that data. Think of it like that ProPublica article. That would be a fantastic result for something like that course. That's sort of what we're aiming for here. So I'm going to make a post on Piazza once this course is in the registrar. This course will be a strict prerequisite for it. So people I know about data science, but haven't taken this course, they cannot get in. I may have something where, if someone's willing to do all the homeworks over break, they can get in, but it's going to be of that level. This course is a prereq for it, and you have to pass this course. So anyone on the board there might want to do it. Oh, and you have to. If you only audited this course, you'll have to do the homeworks to get in there. So it's for people that have taken the course for credit and done the work. I will try to get it hopefully up this week, and I will make a post on Piazza when that's available. So hope to see people there, but I imagine it'll be a much smaller course than this one's been, of course. Okay, we have 23 minutes left. A little bit of time for Q&A, but not too much time because I have a whole other section that I want to talk about final thoughts on the course. So I'm gonna take maybe, I want to say 15 minutes for the last section. So I'm gonna have a very short time now to talk about questions. But let me actually pull up Piazza on my phone here because I want people to be able to write even up to the last minute. I think some of these actually were I think answered in the lecture. So we had a question about further sources for data science. Hopefully that's it. The question actually was also about further readings. To be honest, I don't know a good textbook on data science, at least the way that I view data science. There's tons of textbooks out there. I find them all, the ones I've read, and I haven't read many of them, so there could be some great ones I just don't know about. I find them all a little bit kind of either superficial or somehow just they're sort of too applied. They just go through walkthroughs, don't really cover anything you can't learn in an online tutorial or an online documentation for some package. So I hesitate to recommend specific readings, but that's not, or at least in data science. If you want to learn machine learning, then there's great textbooks in machine learning. Chris Bishop's textbook is an excellent one in machine learning. Just search for it, you'll find it. On databases, I actually don't don't know what the best textbooks are. And so in the more other areas, I don't really know what the best textbook is, but I'm sure there are great textbooks on those areas. But what I'd recommend is don't try to find like a data science textbook or data science piece of reading. Try to find studies you like that ProPublica article. Go look at that, look at the analysis there, see what they did. That you look at the analysis they actually do, and also potentially see what they did wrong as well as what they did right. And then if you want to learn the technical areas, then read a textbook on machine learning or a textbook on databases or whatever else you may have. I think that avenue, I've never like tried to really go through a textbook on data science to really learn it. It all came from sort of other sources that were then useful in data science. Okay, keep using my phone here. The machine learning research was another question, so hopefully I answered that as well. In terms of if you want to do machine learning research, take probably 701 at least, maybe 715 if you really, really want to do machine learning research. And then find faculty in machine learning and ask them what they're doing. Faculty are very open to working with students. They won't give you a ton of time at first because they get a ton of requests about this, so they will probably give you a project and you have to go off and do it, even if it seems like they don't really care. If you come back with very impressive results, they will start caring very fast, and they'll start really being excited very quickly. What drew me to start Smart Energy Systems? Another question that came up here. So I talked a little bit about my own research in this area of energy systems. What got me into energy is just the fact of this being a globally important topic, honestly, and one where there traditionally had not been very much focus on data science. So energy has been a domain where the vast majority of the focus so far has been either from kind of the kind of physics side, right? How can I move electrons better and more efficiently, or like the policy side. So how can what policies can I put in place to actually get this? And there's certainly some data analysis on both those two fields, but there really wasn't an independent kind of thought about how can we use computation and data to improve the efficiency of power. At least it was much less prominent. And so that's kind of what drew me there. And that's also why I think that it's a really interesting and still remains an interesting topic for data science itself. Right, I had the question about the table of machine learning algorithms. Throughout this course, I've given kind of a different take on machine learning than you often will see. And I try to think of it as kind of a unifying view of machine learning. This is the way I think about it, at least. Whereas if you take machine learning, even in 10701, you will see algorithm A and algorithm B, and there will not always be a clear connection between them. So famous example being logistic regression and support vector machines are often taught as wildly different algorithms, right? One is a probabilistic algorithm with maximum likelihood estimation. The other one is this geometric interpretation of margins. They seem completely different, but when you look at what they're actually doing beneath the hood, they're just optimizing the exact same thing, just with a different loss function. One's logistic loss, and one is the hinge loss. And they even look very similar, those two loss functions. They're both linear at the really bad end and go to 0 when you do better and better. So they're incredibly similar, these two algorithms, and they're almost never taught that way. So my view of machine learning is that we have these components. You have a hypothesis class, you have a loss function, and you have an optimization procedure. And you specify all three of those, and that is your algorithm. So the request was that I put together a table that kind of lists a bunch of algorithms and the things. I think I kind of mentioned this in class, but I didn't actually put it online. So I will try to do that. It's been low priority on my list thus far, but I'll try to do it maybe over break or something like that. Put this table up, put it on the website, and maybe make a Piazza post for those that are still following Piazza long after the course is over. All right, moving along. Oh, there's a question on got a lot of votes actually about whether you can, two. One was that what are the most fundamental concepts that came up when I worked in industry? So again, to remind people, I took a sabbatical for a year. So after I also already was faculty here, took a sabbatical for a year at a company called C3 IoT, previously C3 Energy, and I was leading their data science team there. And through that experience, I have to say that this is actually a good question in some sense, because we got about 10 applicants a week for data science positions. I think we hired one to two people, depending on where you count, over the time I was there. So this is a huge number of people that are applying for this that did not have any of the skills you would actually need to succeed at a position in data science. I think part of the problem is that there's just this term is so prevalent right now, and I mentioned this last lecture too, that no one really knows what you mean by data scientist, and so it can mean kind of anything. And so I sort of, when designing this course, it was very much in the back of my mind saying that these are the skills that I would want someone coming into a data science position to know. And I think while it is not, I mean, that is my own perspective. And we want someone that was really a master of these skills. So you have to actually maybe not just pass a homework with them, but really internalize them and know them well. But if you knew that at that level, you would be an asset to the data science team that I was running, at least. And so skills like being able to debug machine learning algorithms and data science pipelines, skills like understanding the similarities and differences between different algorithms, understanding when you apply some, when you apply others, the basic skill of just being able to collect data and gather data and make use of it and clean data when you need to. These things are kind of fundamental skills that people often don't have. And if you do have them, they are incredibly useful from an industry standpoint, and you will be valuable for having these skills. And the last thing, and maybe related to this, is that can someone do that with only an undergrad degree? So I again mentioned this last time. The answer is yes, absolutely. The reason why you see all these requests for people that only have PhDs and 5 years of experience is, as I said, they just are trying to filter out some noise. They're trying to get less than 10 applications a week, or probably this is a relatively small company too, right? Big ones probably have thousands a week. They want to reduce their noise. If you can demonstrate mastery of the skills taught in this course, it is my belief that you will be an asset to a data science, to a company or other industry as a data scientist, and you will be able to do that perfectly fine as an undergrad. I think traditionally, even machine learning, evidenced by their numbers, right? Those had graduate level numbers. These were always graduate courses. The thought, for some reason, was that machine learning is really hard, and people can't do it until they already have their bachelor's degree, and then they study machine learning. I think that's crazy at this point. Machine learning is so prevalent that we should absolutely be teaching it to undergrads, and this was an undergrad course, so I am teaching it to undergrads. And you can definitely do it with a BS, but you do have to master these skills. Okay, I'm over time, so so I'm not going to answer any in class, actually. That was the deal. That's why I posted Piazza. If you have other questions, by all means, come and chat with me after class. I am happy to answer more. All right, so I want to finish up then with a little bit about this course. And somehow, I deleted my last outline slide on final thoughts in this course. But this is now a new section on final thoughts on this course. So this course is wrapping up. You're not actually done yet, right? You have a large portion to do. You have to submit your final project still and the video. So maybe this is better said at the end of the video lecture session. But when we designed this course, the range of topics was intentionally incredibly broad. And you should all feel, I hope, very proud about making it through in some sense, right? I'll mention the other aspects of the course in a second, the fact it was first time and everything on the last slide. But even if it went perfectly, right? Even if everything was perfect, there's been a huge amount of just raw material you've covered, right? So we've covered, web scraping and APIs, relational data databases. You can read the rest, but it goes from everything: data processing, classical learning methods, advanced learning methods, and other things like big data and debugging data science. This is a breadth of topics that I don't see in many courses, and so you should all feel sort of very, very proud, and hopefully, it's also very useful to have some experience now with all these topics. And you should absolutely, when you send your resume to these data science positions, mention the fact that you have skill in these areas now. I mean, don't you want to back it up, but mention the fact that you've done this. And you should feel very sort of, I mean, the people that know all these things are in very high demand, both academically and industry-wide. And if you do feel like you've been able to master these things, you will be in high demand as well. So you should feel very sort of proud about making it through all these topics. I want to mention a little bit also about sort of the interactive component to this. So by far, this course has had more involvement on Piazza than I've ever seen in a course before. I think, like, Eric, do you remember how many posts there were in 213? Okay. 900. So the highest I've ever seen, the highest I've ever seen in my classes before is in the 400s for total posts. I guess 213 or one of those courses, which was a one of the classic large computer science courses, had up in the 900s, and we have almost 2,000. I think we'll break. Hopefully, we can break 2,000 by the time the course ends. Don't take it as an invitation, but just. Though I will remind everyone and people watching on video, please. Your class participation grade is determined by Piazza, and while we have not released sort of the bar, and actually in follow-up thought, we didn't really want to release a strict bar because people would just post junk until they hit the bar of this many posts. I will tell you that the bar is, even despite our maybe fallacy of using standard deviations, but because I'm going to cheat and use whatever metric I actually want, or use it, I should say, put it this way, I will use whatever estimator the standard deviation that I want to use, because we know now that you can do that with other estimators. The bar will be higher than 0 posts for participation, for getting full credit participation, is what I'll say. So if you have not participated very much on Piazza, up to, I won't say how many. I'll say the mean. The mean is like 6 posts, right? Around 6 posts, 5 posts, 5 point something, right? So if you're over the mean, you're fine. If you're under the mean, you may still be fine. But if you are at 0, you will not be fine. So you need between 0 and 5 posts to qualify this. Yeah. Contributions. Yeah, contributions. I mean, we actually value more the answers than the questions. So yes. So you need more than 0 contributions to get full credit. I also want to take a little time and mention the top student answers. So this is what we. Is anyone here? So Emre. So let's thank Emre. I guess we're the only one. Anyone else from the list here? Okay. So Emre, thank you. All right. So I did mention that we really want to not just encourage people posting questions, like private questions to us, because that we're happy to do it, but it takes a lot of time. So we're really thankful for everyone that answered a question, took time to answer other students' questions. We're very grateful. These are the top 5, and there were a lot that were right below this too. So we really want to thank them. It made the TA jobs much easier, but not that easy. So the next slide is going to be, so the top here was 34. So I want to contrast this now with the TA load that we had here. So first, I want to thank Divya. So Divya, you had 261 answers and 470 contributions. So let's thank Divya. That would be, for any other course, the most I've ever seen a TA participate in Piazza. So thank you for doing that. And like I said, that would be for any other normal TA. For any other normal course, this would be insane. But unfortunately, I have to say that your contribution is unfortunately eclipsed by Eric, who we should also thank over there, who had 1,112 answers and 2,000 plus contributions. Eric, for those that don't know, is my PhD student. So I've probably, I owe him a lot in the future. I'm going to have to somehow make this up to him because it's an incredible amount of time and effort he's put into this course. For both of you, though, thanks very much. There was actually a thread on Piazza on this, just about how much people appreciated it. So I want to have some quotes from that just to emphasize this. I'll say to the class, too, that the nature of TAing is that you often deal with the people that are at their most frustrated when you talk with them. So it can be sometimes hard to feel the level of appreciation that the class has for them. So I want to say to Eric and Divya, the class greatly appreciates you. The most common comment I get in lunches is, the TAs are incredible, they're amazing, thank you very much for doing this. We've had 220 students currently enrolled in the course right now. That's despite the look here, right? A lot of them watch it online. So that's currently enrolled. We started out with like 350 or some. We've had 2 TAs. So we had a third TA, but he actually had to drop because his program wasn't going to let him get credit for it. So we had 2 TAs. The normal load for a TA is 1 TA per 25 students. So we've had 1 TA per 110 students. 225 starting the course. So we actually had 330 people starting the course and 2 TAs. So it's been a really amazing. I would not have survived this course had it not been for the efforts of the TAs, and I'm incredibly grateful. Thank you very much for doing that. Let's thank them again. All right, my last slide on this. So as I said here, putting together a first-time course with 220 students, many watching remotely, both actual remote students and students that just don't show up in class, which is very normal when there are videos online. Some of them are actually, the videos were watched a fair amount. I can see who watches them as well, so we can actually get some stats on who watches them. And they're fairly watched. Not everyone watches every lecture, certainly, but they're fairly watched as well. But this is a bit crazy, maybe, right? For having 2 TAs and this load, it's a little bit crazy. I kind of am amazed it's gone this far without falling off the rails at some point. Maybe it has a little bit. And I have to say that this has been a wonderful experience for me and hopefully for you as well. Doesn't always feel that way. There have certainly been times where it's been incredibly stressful. I know that there have been, as I said at the very beginning, but I'm going to repeat again, there's the first-time course, and there's going to be bugs in this course, and there were lots of bugs in the course. And people really kind of, for the most part, took these in stride, and thank you very much for that. Thank you for participating in the course. I mean, the answers we saw on Piazza, it did, though the majority of the course is still, asking questions and getting responses from the TAs. There also was a sense of community that I think built up on Piazza. So I was really happy to see that. People did take pride in answering other people's questions when they could, and sort of pointing out what people thought about when they were asking questions. And I think and again, thanks to the TAs, but I think this sort of made the course from being something completely impossible. If it was just me and 220 students in Piazza, I admit I would not have been able to do this at all. So from dealing with homework bugs, and for TAs putting together the homeworks, I'll put together some, but they certainly did the vast majority of the work in putting together those and grading them and everything, or building the graders for them. From that to the students here who have been very, very helpful in terms of finding errors and very understanding when there are errors, and hopefully we reached a happy medium between trying to stick with the schedule and being a little bit flexible when there were errors. But thank you all. I hope to stay in touch with as many of you as possible as you move forward in your careers. I'm sure you're all going to go in very different directions, and it will be as much as possible. I would love to see what you are doing, and if you are applying things from this course in your careers going forward. So always would love to stay in touch. Thank you very much, and it's been a real pleasure.